All right, it is my pleasure to introduce Natasha Toghramadjian, and I have to go to updated bio. All right, she is a PhD student at Harvard University studying geophysics with a focus on highly hazardous earthquake sources and their complex 3D ground motion effects. Her current work centers on characterizing fault systems in downtown Los Angeles to anticipate likely future rupture scenarios. Funded by a US Fulbright research grant, she spent 10 months in Armenia as a geophysical researcher designing a collaborative statistical seismology study on reservoir-triggered earthquakes, aiding in the development of a new regional seismic network to study the subsurface structure of the Caucasus Mountains and investigating how international scientific collaboration is shaped by regional politics. She has led several experimental field studies in the Seattle Basin and Fault Zone, and her research is supported by the NSF Graduate Research Fellowship and the Harvard Ashford Fellowship. She is a student member of the Society of Catholic Scientists, and please offer her a round of applause.
So hi everyone, it's been very nice to meet many of you and talk with many of you, and I'm excited to talk a bit today about the Catholic contributions to seismology, my own field, as well as some of the human consequences of earthquakes, which lead us to consider them from perspectives that are beyond purely scientific. So there stands a strange sight today in the city of Lisbon, the roofless Carmel convent. Now, this missing roof is intentional. It serves as a reminder of an event that took place almost 3 centuries ago, but remains today an image that poses a grappling challenge to both the faithful and scientists alike. Now, this event, it was the estimated magnitude 9 Lisbon earthquake of 1755, which struck the Portuguese capital on All Saints' Day, releasing an energetic equivalent of 32,000 atomic bombs. In mere minutes, seismic shaking brought down the city. Many faithful observing the holiday mass were killed inside collapsing churches. And this earthquake also then generated a massive tsunami, which inundated Lisbon soon after, drowning thousands more people. Fires ignited inside falling architecture, and the city was an uncontrolled blaze for the next 5 days. So this is a very realistic depiction, even though it's artistic. It looks quite the doomsday picture, but that really encompasses the different cataclysms that came together in this huge earthquake. And so up to 60,000 people had been killed, and nearly every Catholic church in Lisbon had been destroyed on a high church holiday. European Protestants interpreted this as a sign from God, punishment of the Roman Church. In England, the newspapers termed the earthquake a Catholic catastrophe. So, the 1755 earthquake, although it was a theological grapple, it also shook more than the ground. It radiated shockwaves through the philosophical circles at the time, who were forced to come to terms with the question, what is man's position relative to the laws of nature? Now, this is an ancient question, but each generation asks it again, including the Enlightenment thinkers who were profoundly influenced by the earthquake. These philosophers, Voltaire, Kant, Goethe, are often remembered as modernist, secular harbingers of existentialism, but their reactions to the Lisbon earthquake in many ways echoed Catholic understanding of natural disasters. In Luke 13, the disciples grapple with a similar catastrophe. A tower had collapsed on Jews who were on a pilgrimage in Jerusalem, worshiping and praying to God. Why them? Had God chosen to punish those who, by all appearances, were his most devoted servants? Were the 18 killed by this falling tower worse than the sinners who were spared? In the aftermath of the Lisbon disaster, Voltaire returns to the same question, echoing the disciples. Is there a connection between calamity and iniquity? Goethe is shaken by how the natural world treats the good and the bad alike. Kant, reflecting on our universal fate of earthly death, questions how the manner of death can matter when compared to the eternity that we're promised. So it was in this philosophical ferment in the aftermath of Europe's first modern disaster that the science of seismology was born, and it would be carried into its current form by Jesuit Catholic priests. So while London's newspapers were gloating, The Jesuits were already laying the groundwork for a more scientific, and as I will explore, a more Christian approach to living with seismic activity. The Society of Jesus, founded by St. Ignatius of Loyola in 1534, began as a small band of well-educated young men, determined to bring the message of Christ to the edges of the earth. Jesuits were charged to be excellent in secular pursuits as a means of upholding the excellence of the Church. Loyola charged his brothers to celebrate the full range of human intellectual power and achievement. Jesuits were compelled to find God in all things, to seek out Christ in every dimension of life, with no enterprise being merely secular. Furthermore, Jesuits were to consider the whole world their home, to travel through the world and live in any part of it, wherever held the opportunity to give greater service to God and help souls. Aptly nicknamed God's Marines, Jesuits were the disciplined vanguard of Rome, and they soon became known as vigorous missionaries of Christ, who almost single-handedly established the faith in numerous regions of the world, with a commensurate impact on the secular world. The Jesuit vows and values meant that Jesuits found themselves at the edges. Whether these edges were the furthest flung geographic corners of the earth or bold scientific innovation expanding human knowledge, Jesuits were frontiersmen, and no place was too foreign or far. They were the first world explorers with higher education, the first Europeans to venture into the interiors of Mexico, Mongolia, the Amazon. Here you can see them depicted in everywhere from Madagascar to Japan to China to the Philippines. Jesuits were also the first Western scientists to enter into contact with China and India. By the mid-18th century, Jesuits directed 30 of the world's 130 major astronomical observatories. Christian faith was said to have entered China, helped by the hand of astronomy. Jesuits also believed that an excellent education was one of the best ways to both serve the Church and improve individual lives. By the 1700s, the Jesuits were operating more than 800 universities, seminaries, and secondary schools around the world. Mathematics was an especially important part of the Jesuit curriculum because it underpinned critical topics from physics to geography to navigation to military science. Jesuits teaching these subjects thus quickly became practiced experts themselves. One exemplary anecdote of this iconic Jesuit pursuit to know God's creation is the scientist Athanasius Kircher. In 1631, after an explosive volcanic eruption in Mount Vesuvius, he had himself lowered into the active volcanic crater to observe its features as close to eruption as possible. He illustrated his observations, shown here, and NASA actually recently confirmed a few of his observations, such as a central heat source in the center of the Earth. So embodied in Kircher, it was this Jesuit ethic, this combination of rigor in the natural sciences and math, and a willingness to go to the ends of the earth that uniquely primed the Jesuit order to make unmatched contributions to modern earthquake science. So now, we're going to come back to the Jesuits in a bit, but I first want to set up some modern geophysical methodology and several case studies from my own research in order to contextualize the contributions that Jesuits would later make to seismology. So in terms of basic geophysics, when an earthquake occurs, for it to be located, it needs to be detected and measured by at least 3 seismic stations. And once it's detected, you can see where those 3 radii intersect. That gives you the earthquake epicenter. And the better the distribution of stations, the more accurate your location. Now, if we consider earthquakes in 3D on the right, we can see that the further a seismic wave travels along the surface of the Earth, from the epicenter to the recording station, the deeper it samples the interior Earth structure. So you can see the longer waves cut in closer to the core. You can see S waves, for example, are not transmitted through Earth's liquid outer core. That's because liquids cannot be sheared, so they're not propagating through. Whereas P waves, which are compressional, are refracted and deflected in the liquid outer core. Meanwhile, surface waves travel only along the Earth's surface. So, the unique characteristics of different seismic waves and how they travel means that earthquakes can tell us quite a lot. But for a wave to tell us anything at all, for it to be more than just a catastrophe, it must first be observed and recorded. As you can see, it's the recordings at multiple stations sampling the entire hemisphere that allow us to tease out the patterns in seismic waves. So this is the underlying reality of geophysics. that in order to investigate a planet-sized natural laboratory, in order to observe what we cannot physically access, which is sort of the main defining theme of geophysics, that our observation is physically inaccessible, we deeply rely on instruments installed at the surface. But you don't have to just take my word for it. I can walk you through a quick whirlwind of past field experiments to demonstrate that the quality of geophysical research we can do directly depends upon the quality of our instrumental networks. And these allow us to see into the Earth. So, we'll start with a few active volcanoes just outside of Guatemala City. So this is Volcan Pacaya, which is looking relatively peaceful here, which belies its destructive power. In 2010, Pacaya erupted, and while fortunately no one was killed, lava flows and explosive projectiles destroyed homes and injured people. Here you can also see how volcanic bombs penetrated the corrugated steel roof of this chapel. A research initiative in the wake of this eruption was to scout out sites to install a network of seismovolcanic sensors around Pacaya, which would increase the ability to detect eruptions in advance, giving residents more time to evacuate. And the fieldwork for this task entails everything from cutting through jungle bush to finding translators who speak the local Mayan dialects. And I show this again to illustrate that the days of trekking, planning, and digging are worth it to geophysicists because sensor geometry and location directly determine the quality of science we can do. Now, we can take a case where we were not able to deploy seismic sensors. This was Volcan de Fuego. And it had been continuously erupting for years, so that while we could trench in the pyroclastic ravines, which you can see those carved out lava flows, we could go in there and collect ash samples. However, it was too dangerous to deploy geophysical sensors. In 2018, Volcan de Fuego violently erupted, destroying several towns and claiming 165 lives. Had there been sensors, the eruption could have likely been detected earlier, and the government would have been able to act and evacuate people in advance. So this is an unfortunate demonstration of the same point, that geophysical networks are useful and necessary not only for academic research, but also for disaster prevention. Next, we'll jump to another continent and look at the Caucasus Mountain Belt, a convergent tectonic plate boundary. So our goal here was very different from the goals on the volcanoes. Here we wanted to investigate the geodynamics of an actively forming young continental collision zone. And again, with this very different scientific objective in mind, the key is the same. You can see here a map of the seismometers that we deployed to cut a transect across the mountain range. And this densely spaced array would allow us to image the subsurface structure of the mountain belt, similar to the way an X-ray works. And lastly, we'll jump to urban Seattle, where the common theme continues, this time for studying how shallow rock layers will behave in urban settings during future large earthquakes. So for this, I designed a multi-phase field study, reaching out to local schools, churches, and businesses to host our instruments. And you can see here in this first network that 3 of the 10 stations were hosted by Catholic churches and schools, and they were all too happy, of course, to facilitate our study. Some of them participated in the digging and hung out with us, and they showed us inside their churches and their schools, so it was a very pleasant human dimension to the work that is very relevant, and we keep in mind why we're doing these studies, because of the people that live in these dangerous areas. And then phase 2 of the experiment consisted of 4 profiles of seismometers crossing the Seattle Basin Edge and Fault Zone, which you can see in black. Now, one might wonder about the feasibility of deploying 100 seismometers in downtown Seattle, each spaced only 2 to 3 houses apart. In fact, the local seismologist thought this would be impossible, but after weeks of phone calls, mailed letters, and media outreach, I was able to coordinate the most densely spaced seismometer array to sample a basin edge. And again, it's the quality of data, which you can see highlighted here in the 3D seismic wave field. You can see the clean signal-to-noise ratio, clear seismic wave signals that we're looking for, directly dependent on the way we design the sensor array. And that's why geophysicists devote so much time to this. So, now that we've thoroughly established the critical importance of seismic networks, we're going to jump back to the Jesuits. And one of the greatest Jesuit contributions to seismology is perhaps best visualized in this map of the worldwide locations of Jesuit seismic stations. Jesuits, grounded in their past centuries of work pioneering in the natural sciences and living out missions on every continent, organically established scientific centers wherever they went. Several Jesuit stations in Africa, Asia, and the Middle East were the first and only scientific observatories in those areas for years. Jesuits trained local personnel to work in observatories with them, thereby also providing some of the first scientific formations in those countries. And at one point, they were operating over 50 stations worldwide. So we can appreciate how invaluable of a scientific contribution this was, especially given where the field of seismology was at this time. Tectonic plates themselves had not even been recognized until 1915. And looking at the dates, you can see that many of these were deployed well before that was even on the horizon in the field. So it's unsurprising that the seismology was soon came to be known and called the science of the Jesuits. Now, this instrumental leadership was especially strong in the US, where Jesuits are single-handedly responsible for developing the first continent-scale seismographic network of uniform instrumentation. The Jesuit Seismological Service, founded in 1909, conceived an idea by Father Frederick Odenbach. As you can see in his letter here, he threaded the needle in early 20th century seismology. He said, if we can get a number of our colleges to host these stations, we would be in a position to do the great thing in seismology, to organize a system of observatories with the same kind of instrument, handled in the same way, and these stations would be fairly well scattered over this continent. And the more extensive this network, the greater the value of the seismograms that we can capture. So, this idea came to fruition as 16 identical seismographs were hosted at Jesuit colleges from Brooklyn to St. Louis to Spokane. By 1911, Jesuits operated over a third of the 44 seismographs in the United States. Then, at the urging of the scientists of the National Research Council of Washington, this network was revitalized and succeeded in 1925 by the Jesuit Seismological Association, a major center of seismological research from the 30s to the 50s, inaugurated by Jesuit James V. Maselwain. Now, Maselwain is undoubtedly the most renowned Jesuit seismologist in history, and with good reason. A true pioneer of American geophysics, he received the first PhD in seismology in the US. He soon after founded the first university geophysics department in the Western Hemisphere. He established the first chain of seismographs in Northern California. He published the first theoretical textbook on seismology in the US, and he served as the president of the American Geophysical Union. Maselwain's energy for geophysics came in part from his recognition that Jesuits were natural seismologists. As he noted, men are lacking in seismology because of the severity of the training required. One must not be only a good experimental physicist, but a good mathematician and geologist as well. Here is our opportunity. So beyond his historical, institutional, and pedagogical contributions, Father Maselwain was a leading figure in cutting-edge seismological research. You can see just a sampling of his groundbreaking geophysics contributions. This is just a smattering of the articles that he published. And he also was deeply committed to the educational development of seismology. So he completed annual surveys on the state of geophysical education in the country, strategies for organizing physical data and upkeep. And so he really encompassed all the dimensions of trying to move this field forward. In recognition of his contribution to American seismology stands today in the American Geophysical Union, which is the largest professional organization of earth scientists in the world. They annually give out the James V. Maselwain Medal in his honor to award scientists of outstanding ability. Now, beyond Father Maselwain, there's too many other Jesuits to count, but you can see there's other very diverse contributions to the field. But there were two that I'd like to highlight who stood out to me for the living energy with which they inhabited the intersection of their science and their faith. The first is Father Daniel Linehan, known as the earthquake priest. He discovered one of the 4 types of seismic waves. He completed renowned voyages to the North and South Pole, measuring ice cap thickness. Here you can see him performing Mass on an Antarctic expedition boat. He performed refraction studies beneath St. Peter's in the Vatican for archaeological investigation. But you can see from his journal entry here that it was an abiding love of God that drove his passion for science, and he was priest first and foremost. He writes, "Today, when I read my seismograph, there were only two who knew that rock was down there, under 60 feet of water. Only God and I knew. And to think this is the same God who came down to our altar this morning, the same God who made that rock, who made all rocks in the world. I would give up all my seismology to celebrate one such Mass." Next is Father James Scahan, who was a visionary in the tectonics of complex mountain formations, and he understood science as another way to hear God's voice. He claimed that what he does as a scientist is no different from what he does when listening to the cosmic word of God. Now, Father Scahan got to live this out, this priest-geologist ideal, in a uniquely exhilarating and beautiful way in 1970, when an undersea volcanic eruption off the coast of Iceland formed a new landmass. Father Scahan organized a NASA-funded expedition with dozens of scientists flocking to the island to observe how plants and animals come to populate new land. He also took the opportunity to celebrate the first ever Mass on that piece of land and ended up baptizing one of the scientists on the voyage. So here we see the Jesuit ethic in full form, with Christ literally brought to the edges of the earth. However, while we delight in the earth's beauty and mystery and order, and find God in all things, a simultaneous theme that we've seen from Lisbon to Guatemala is the earth's destructive potential. A point of reflection here from Pierre Desjardins, as we consider both the beauty of a newly formed volcanic island burgeoning out of the sea and the death tolls that the very same force can cause, is that while God is pure good and nature is God's creation, nature is not God. It has equal energetic capacity for human help and harm. The mountain and the pit, they coexist. If we were mere rocks, mere physical matter, earthquakes wouldn't bother us. They would be a natural part of our life cycle. But we see the horror that can occur when we are involved in earthquakes. For example, the magnitude 6.8 earthquake that struck Armenia in 1988, which at the time was defined by very poorly designed Soviet construction and project housing. This earthquake killed up to 30,000 people, most of whom were children, as hundreds of schools collapsed during the school day. The earthquake struck in the morning. This was a terrible, devastating earthquake. And in the aftermath, 1 in 7 remaining Armenians were left homeless. So our ability to see the horror of earthquakes is the same thing that tells us that there is a God who is loving, not capricious. It is precisely our awareness of and revulsion at nature's destructive capacities that illustrates that we are not fully of nature. We come from somewhere else. To paraphrase C.S. Lewis, we do not look at the human effects of an earthquake and say, this too is God. Rather, we look at the effects of an earthquake and feel a sense of wrongness, injustice. And we are capable of that feeling because humans are not ultimately just of this earth. And this is what makes Christianity different from Buddhism or pantheism. We are absolutely in touch with nature, as we've seen through the Catholic pioneers of natural sciences, but we do not worship it. Earthquakes give us a heightened, sharp moment of reminder that we were ultimately made for somewhere else. As Saint Therese of Lisieux said, the world is your ship, not your home. To quote Lewis again, Christianity is a fighting religion, and that is why we approach earthquakes with all of our faculties, from scientific investigation to learn from catastrophes past and present, to applying seismic engineering to address calamity's future. And I think that the Catholic response to this precarious position is embodied in places that I've spent a lot of time thinking about faith and earthquakes, namely ancient Armenian churches, almost every one of which has been destroyed and then faithfully rebuilt. Ancient Armenian Christian architects were charged with the task of balancing their expressions of faith in delicate stone constructions with the lateral and vertical motions posed by frequent earthquakes. From the 4th to the 6th centuries, they refined an architecturally ingenious method of design, creating crack-resistant concrete from local volcanic ash mixed with rock fragments, egg whites, and lime. and purposely assembling stone blocks with beveled edges and non-uniform size and alignment, which produced highly resistant surface cohesion and resisted blocks falling out of the wall during large earthquakes. Other features were introduced over time, experimentally seen to mitigate earthquake ground shaking and its effects on the structure. Features you see here, which seem to blend in as simple decoration, actually embody a good deal of ancient experimental seismic engineering. So those long, narrow divots that you see in the front and the sort of oblong holes are not mere decorations, but as they are explained to me, or when you go there and visit, they're actually features built in response to past earthquakes that have destroyed this monastery. So these churches, built of rocks, take the very stuff of our planet, our earthly home, and transform it into a spiritual home. Even though every Armenian church has been destroyed at least once, by earthquake or by enemy, these spiritual homes are faithfully rebuilt, each time a little bit more resilient, each time with more insight into how we can worship God on a planet that is both beautiful and dangerous. And to me, this history of design, collapse, and thoughtful and faithful renewal is a fitting metaphor for the path of a Catholic scientist, and for the way earthquakes ultimately teach us how to be Catholic. Thank you.
Thank you for an excellent talk. All right, we have time for questions now.
Thank you for that beautiful talk, and that's an incredible church. So Father McIlwain was, he's sort of like the Georges Lemaitre of geophysics, but sadly, when you look at the McIlwain medal, and you can Google on it online and stare at it, you're hard-pressed to tell that he's a priest. He actually looks like he's wearing a turtleneck rather than a Roman collar.
Yeah.
And nowhere is the SJ put after his name, and so I like to say that the American Geophysical Union has laicized, effectively, Father McIlwain. Imagine the impression that the McIlwain winners would have, and perhaps some of the thoughtfulness that might arise if they actually knew that the person whose medal, after whom the medal has been named, was a Jesuit priest. I think that would be a wonderful thing, and it's kind of a shame the AGU has done things that way, but that's part of why the society is here today.
Yeah, I completely agree, and one small bright blip is Peter Hybers won the McIlwain Medal a few years back, and of course you give an acceptance speech, and I read his, and he very explicitly said how meaningful it is for me to win the McIlwain Medal because I discerned almost becoming a Jesuit priest. And so he brought this attention, and everyone was like, why is that meaningful? So he was like, because. So there was a brief moment of recognition, but I completely agree. And well, the Seismological Society of America also gives out the Jesuit Service Award every year. So that's a little more explicit in its title, but.
You began your talk with a discussion of the Lisbon earthquake of 1755 and kind of ended it with this discussion of the better construction. Somewhere around 1700, in a town called Cusco in Peru, the Spaniards took over and built an elegant cathedral on top of, and replaced, but on the basis of something that the builders of Machu Picchu had done. Presently, there was an earthquake, and the whole Spanish apparatus, cathedral and all, came tumbling down, but nothing of the Machu Picchu builders ever was hurt at all. And that tells me that some people anciently knew a lot more about earthquake-proof construction than we ever did. And I wondered if there were important lessons learned from that, even though it wasn't applied by 1755 in Lisbon. Was that knowledge ever really discovered or understood and put to use?
Yeah, that's a great point. It reminds me of something I read about earthquakes in Liechtenstein recently. And all of the new construction came tumbling down, and it was well built. I mean, it's a developed country, Liechtenstein, and it was made with seismicity in mind, but all of the wooden-framed ancient houses stood standing, and they were very puzzled. So, I mean, I think about it like to what point you have to get to be mixing egg whites into your building. Like, they really must have been doing a lot of trial and error. So I think there's something, there's a testament to their determination to keep their church standing in some of the most dangerous places.
That was a great talk, very inspiring. What sort of warning, or I guess time span, do we have now for earthquakes, and how is that improving recently with modern computing?
That's a great question. So there's a lot of work that's being done on earthquake early warning. So essentially the first wave that comes, which you saw in the interior of the Earth, is the P wave, and that's compressional, so you don't feel it. However, with very sensitive seismic sensors, which are being more recently developed, they can detect it fast enough, triangulate the earthquake, find out where it is. Now, if an earthquake occurs offshore, that earthquake energy has to travel onshore to where the people live. And that would mean that you have maybe a minute, maybe some seconds, depending on how far away it is. However, if the earthquake that occurs is on a fault that runs through downtown Los Angeles, such as the one I'm currently working on, which I didn't talk about here, it's virtually infinitesimal because the ground ruptures beneath your feet. So traveling to the area it would devastate is not part of that scenario. So it really depends on the relation of the endangered area and the earthquake hazard, but there's a lot of really good machine learning work being done to do what we can for those more distant earthquakes.
Thank you so much for your talk. I'm actually blessed to have been born and raised in Lisbon, so the earthquake is very much in our memory and past.
Wow.
And one important thing is actually that it was 4 years after the earthquake that the Jesuits were expelled from Portugal. It was the first expulsion, royal expulsion, and then it lent, 2 or 3 decades later, they were suppressed by the Pope. So the earthquake kind of played a role with the meanings that were attributed to it. One interesting thing, though, is that when they came back, when the Pope reinstituted the Society of Jesus, it was really then that seismology seemed to have taken hold on them, right? So in Lisbon, however, what is interesting is that most of already in the 19th century, the kind of things that they do is at the high school level. So they have very interesting high schools, top level, even like the Masonic and atheist people would send their kids to these Jesuit schools. And they would do research there. So they had novel research going on in high schools. My question is, what about the US? Like you have these seismological stations in Jesuit colleges, as you said, but were they also doing that at the high school level or not?
So that's a great summary, and I'm glad to hear from someone who has it so close to home. I didn't mention the suppression of the Jesuits, which happened about 5 years after the earthquake, so there was sort of this hiatus, and then, like you said, it sort of aligned with modern seismology developing when they were active again. Now, in the US, it's almost a remnant. Part of the Jesuit vow is a vow of poverty, so they were constantly competing with better funded government institutions, high-level research institutions. The US Meteorographic Survey really wanted to become the powerhouse in seismology stations. So they were always sort of fighting the scrappy fight to stay in science. And there are a lot of Jesuit colleges today that have seismometers. Like I went to Boston College. I studied geology and geophysics there, which has a seismometer, and that's how I got introduced into my science. Georgetown still has a seismometer. And there's several small observatories. They're not anything today like the powerhouses of seismology, but they're important, small, sort of historical sites that are definitely functional. And if they're not papered over, like you mentioned at AGU and other parts of scientific culture today, I think they continue to make an important presence.
Hi, so you mentioned a connection between danger and beauty, and that makes sense to me. I think like the burning bush or the Odyssey with the sirens, or like the book of Job when God's berating Job. And I was wondering, in the earthquake in the tsunami that took place in Lisbon, do you see that same beauty there, or how do you see that in the presence of earthquakes and a lot of the destruction they cause also?
Yeah, so I think earthquakes have capacity for danger and beauty based on where they happen. So, for example, in Russia, there's a big mountain range, the Ural Mountains, and they're inactive tectonically. They used to be an active plate boundary. So today, we just see them as a beautiful mountain range. But you can imagine if while they were forming, people were around there, they were very devastating and frightening and dangerous. So I don't see beauty in catastrophe. I see beauty in rocks and mountains, but obviously everything on earth has the capacity for helping and harming, and only God is pure goodness to me.
We're good? Okay. All right, if we can thank our speaker again.